Sure. I'll start sharing my screen, and hopefully you will be able to see it. So can you see my screen?
Yes, we can see.
Perfect. Perfect. So let me get rid of this. That's great. So and put it on play. Okay. So can I go ahead, Okun? Yeah.
All right, we can go on.
Thank you so much. So thank you for having me at this school, and thanks to all the attendees, either remote or in presence, for being there. So I'm Mauro from the University of Palermo in Italy, and retaining some links with my previous institution, Queen's University in Belfast. And so I agreed with Osgur to talk about what we can do with the combination of machine learning methods and quantum dynamics to achieve goals that are relevant for quantum information processing, quantum technologies, and given the topic of the school, which is programmable photonic quantum computers, also highlight or illustrate what we can learn on the dynamics of photonics platforms and systems. So let's have a look at what will be the structure of the talk. So we'll start very gently and slowly with a very bad introduction to machine learning for quantum physics. Okay, so at least providing the motivation for why we would gain a bit in combining machine learning techniques and quantum dynamics. Then I will illustrate as an example the problem of so-called quantum gate synthesis. Okay, so which is the problem of realizing a given transformation, a desired transformation, and I will illustrate how the use of machine learning can help us, can assist us in achieving the task. Then we will move more towards the experimental part of the talk, or at least the part where I will touch upon experimental results, which is the use of machine learning for quantum state engineering and quantum property validations. And for these problems, I will illustrate the results for these parts of the talk. I will illustrate the results that have been achieved in a few experiments run in the group of Fabio Sciarrino at Sapienza University of Rome, dealing exactly with a photonic quantum computer. So let's dig into the motivations and see what we can benefit from when we combine quantum mechanics and machine learning. And in order to do that, I'll need to introduce or discuss a bit of the good, the bad, and the ugly of quantum state engineering. So namely, the fact that when you are interested in engineering a given state or achieving a certain dynamics, the following three things are, so to say, ingredients that you cannot do without. Okay, so the annoying bit, the bad bit, and then the ugly bit of state or transformation engineering. What is the annoying bit is the fact that it will take, so synthesizing states, engineering states, or synthesizing transformations will require an exceedingly large amount of time that grows with the size of your computational problem. So the more complex the problem you want to solve, which means the larger the resource, the quantum resource that you want to engineer, the more time you will need in order to synthesize it, to achieve it. The bad bit is that typically these experiments require quite a lot of money. So they're incredibly costly because you will need, in a way, to ensure a very high degree of accuracy in the implementation. And needless to say, accuracy depends on resources, and the cost of running experiments that are accurate to the right level, so basically to the level of making the processing of information robust against the effects of errors, costs money. And the ugly bit is that even investing a lot of resources in terms of time and money, you might not end up having it right overall and altogether. these plots, the plot that I show here at the bottom right of this slide, has been taken from this paper by Antonio Mandarino and Matteo Paris a few years ago, where these guys show that if I'm interested in engineering the entangled state of two harmonic oscillators, and the state, say, has a fixed number of excitations in it, or photons in it, and this is the capital N that you see in the vertical axis of the plot, and at a given degree of mixedness, which you can assimilate to an effective temperature or inverse temperature beta, which you see on the right-hand side, then you end up having a region of separable states, which is this blue or purple colored region that you see in the plot, and a region where you give me the entangled state that you want to achieve, and I can achieve it with a fidelity, so with an accuracy, so to say, that is in excess of 99%. And that's the red, say, Gaussian-like or Lorentzian-like shape that you see in the plot. And while I would like the region of separability to be disconnected from the region where the target states are achieved with high enough fidelity, then you can see that there is a region of overlap. And that overlap is not even small, which means that despite I'm able to achieve a state that is incredibly close to the target state that I would like, and the state that I would like is an entangled state, there are values of n and beta that could lead me to a state that is separable instead. So even if the quality of my synthesis was really, really good, 99% of fidelity, then I might end up with a state that I don't want, which tells us that really the problem of state engineering, the problem of synthesizing a given property of in a quantum register is an exceedingly complicated problem that requires a lot of very valuable and very costly resources. So can we do better if we somehow abandon the traditional way to achieve state engineering or gate synthesis, and instead we resort to some very well-established techniques in machine learning? And that's the scope of the talk. And in order to dig into that, I'll need to introduce very quickly what is the so-called bubble structure of learning, okay? So let me abuse a little bit the field and say that this blob here represents for me computer science, and here at the corner of computer science is artificial intelligence. There is an abuse of terminology these days. Even media use the word, say, the terminology artificial intelligence for basically anything having to do with digital technology. But artificial intelligence in reality is the study of intelligent agents. And what is an intelligent agent is a device, in a general sense, that explores the environment around it and acts so that it maximizes the chance that it has to achieve in a successful manner a given goal. Okay, so it's an opportunistic agent, a device that really moves in such a way that a given goal is achieved in the best possible manner. And there, at the corner of artificial intelligence, somewhere within this domain, is machine learning. And defining what machine learning is a lot more complicated. In a very, very superficial, rough way, we can say that machine learning seeks patterns in data in an empirical manner, and does that without enforcing a given model on the data themselves. Okay, so basically, it's a way to infer patterns without forcing a model, so without driving a model to them, but making use only of a data-driven approach. So the patterns are learned from the data to make sense of previously unknown inputs, and there is no model fitting, basically. So there is no comparison with a previously pre-cooked digested model that we might think will be appropriate to explain the patterns that we are interested in. This definition of machine learning, or what I think is the closest thing to definition of machine learning, was given by Arthur Samuel in the 1950s, when he said that the machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. And that gives you the measure of what this data-driven versus model-driven approach is there for. Over the years, probably in the past 5 to 10 years, probably less, the combination of machine learning with areas that are close to quantum has been significant. No? So there have been examples of the deployment of techniques for machine learning in quantum chemistry, for the design of materials, in quantum information, and that is the area that I'm interested in, and certainly in quantum statistical mechanics. And if you open, I'm sure, if you open media or if you open the archive, you would have absolutely no trouble in finding a paper or papers mentioning quantum machine learning. And I myself had some troubles understanding what quantum machine learning is. I don't think there is anything like quantum machine learning as yet, while on the other hand, we have two very well-established perspectives on the combination of machine learning and quantum. And one is what I call the quantum for quantum approach, and the other is the classical for quantum approach. In the quantum for quantum approach, the goal is to develop new algorithms, genuinely quantum algorithms, that should be useful to solve problems of machine learning using quantum information processing. So if you think a second about that, it should become apparent that this is basically very, very close to the problem of finding quantum algorithms, and is indeed a problem that is as difficult as that of coming up with new, genuinely provable quantum algorithms. On the other hand, the classical for quantum domain or approach uses consolidated, very well-established machine learning methods, classical machine learning methods, to run quantum problems more efficiently, more effectively. And this is where most of the research done so far in this domain of quantum machine learning, this abuse of language, this area at the crossroad between machine learning and quantum information processing have been generated. So most of the research done so far in the area of quantum and machine learning addresses the perspective of classical for quantum. So the use of classical machine learning for quantum problems. A bit of literature that can explain what I said very, very badly until now in many more details and much better than what I did. So have a read at these resources, at these references, if you are curious, if you are interested in exploring the possibilities of this classical for quantum approach, and whether or not a quantum for quantum approach is indeed possible. And now, just to provide an illustration of what we can do with this classical for quantum approach, let me address the problem of quantum gate synthesis as a paradigm of what classical machine learning tools can do for a quantum problem. And these four gentlemen are the guys that worked with me to make the results possible. So Sugato Bose at University College London, Leonardo Banchi, who is now in Florence in Italy, Luca Innocenti is with me in the group in Palermo, and Alessandro Ferraro was in Belfast with my group at the time this paper, and the paper that you see listed at the bottom of this slide has been was published and is now at the University of Milan. Okay, let's see what is the problem in very, very simple terms. Okay, so let's see. Let me illustrate it in very simple manners. Okay, so the gentleman that you see here is Sami. Sami is my son, and the photo was taken when he was 3 years old. And we should take Sami as a typical learner. Okay, the the typical guy that wants to learn how to achieve a given task, how to achieve something. Great. What is the problem that Sami wanted to solve? Sami wanted the pirate ship, okay? The Lego pirate ship. And he wanted to build it having the Lego bricks that he had at home. The problem is that he didn't have all the bricks that were needed. No, you can see various shapes and forms of bricks in the construction of this pirate ship. He only had 15 bricks of these colors: one red, red colored, green colored, blue, and yellow colored. So the question was, and the question that we try to address and that I'm trivializing is, can Sami engineer a pirate ship using only red, green, blue, and yellow colored bricks and 15 of them at most? So now, moving the question towards a less trivial and a more systematic manner, the question that I want to pose is this: can I synthesize, so can I engineer a given transformation, a given gate G, that I need in order to solve a given computational task, quantum computational task, using a generator HG that only takes operations that belong to a given set lambda, okay? So, gamma. So I have gamma as a set of allowed transformations, and I want to build a generator HG that accomplishes exactly the gate G that I need to solve my computational problem. So again, because I'm a simple-minded person, let me draw an example to illustrate what I really want. So this heptagon, red heptagon that you see there, is the desired transformation that I want to achieve. Sami's pirate ship. That's what I want to achieve. And I know that what I would need in order to achieve that transformation is this set of elementary gates. I will need pentagons, I will need triangles, I will need green squares. If I combine all these ingredients all together in the proper manner, I will be able to achieve the red heptagon that you see on the left-hand side, so the desired transformation. But I don't want to use all these complicated gates, no, these triangles, the squares, the pentagons. So I don't have all these various different Lego bricks. All I have are the 15 bricks that Sami was given with, okay? So the set of transformations that I have available is this set gamma, and gamma constitutes, so is built only of these green squares. So can I put together green squares in a suitable way so as to achieve a red heptagon? Can I put together these elementary transformations, which are maybe dictated by the capabilities at an experimental level, to realize a gate that I really need to solve a computational problem in an exact manner? And the answer to this question is the following. So if from now on you want to detach entirely from this talk, you are free to do it, but that's the take-home message that you should at least bring with you, okay? So the answer to the question is in the positive. I can do that, provided that three conditions are met. And these three conditions are easy, and we are going to state them in a second. And then what I will do is to illustrate how supervised learning can help us optimizing the problem of meeting these three conditions. So fulfilling these three conditions that guarantee the possibility of generating gate G from the use of only operations belonging to subset gamma. Okay, let's have a look at which are the three conditions that I need, okay? And in order to do that, I need a little bit of very, very, very simple maths. So this is nothing beyond what an undergraduate student that has taken an elementary course on, say, a course on elementary quantum mechanics should have seen at least once in their career so far. So let's say that G is the gate that I want to achieve, and HG is its generator, okay? So given that G is unitary, it can be written as e to the I HG. And needless to say, I can spectrally decompose my unitary, no? So I can find the eigenvalues lambda of my gate G, and U is the transformation, in general is an orthogonal transformation that allows me to build up my unitary starting from the diagonal matrix lambda. I can take a logarithm left and right hand side of this relation, and therefore get an expression, an effective expression for the generator HG. That depends entirely on the eigenvalues of my unitary. And now this generator in general will contain both feasible, so both allowed, and unfeasible interactions. So both bricks that I have and Lego bricks that I don't have, okay, or that SAMI doesn't have. What I want to do is to eliminate all the interactions that I don't have available, that are unfeasible, and only use my feasible ones, my allowed ones. So my goal is to construct a different generator, HG tilde, built using only the green squares, but in such a way, built in such a way that its complex exponential gives me exactly G, not an approximation of it, but exactly the gate that I would like to realize. What do I don't want? Okay, so which are the constraints that I'm putting into this problem? I don't want time-dependent Hamiltonians. Okay, I don't want to have time ruining or complicating my problem. Okay, so you know, I presented time as the annoying bit of the problem of gate or state engineering. I don't want to have ancillary systems, so I don't want to let my register grow even more. That will cost a lot of money. So I don't want to address the bad part of the state engineering and property engineering problem. And I don't want to implement complicated quantum control, because as good as I could be in realizing quantum control, it will never be perfect. And if it's not perfect, I might end up having to face the ugly bit of state and property engineering. So basically, by requiring no time dependence, no ancillary system, and no complicated quantum control, I'm basically excluding the possibility of having to deal with the bad, with the annoying, the bad and the ugly bit of my problem. What do I want? And these are the three conditions that I promise you I would have illustrated. So I would like a generator that contains only my feasible interactions, so my green squares or my colored bricks that SAMI has at home. I want the new generator to commute with the old one, and I would like the spectrum of the difference between these two generators, between these two Hamiltonians, to be an integer number of times of 2 pi, okay? So if you meet these three conditions, and they can be justified in a mathematically rigorous manner in a little bit of time, but we are not going to go through it. If I meet these three conditions, then you can achieve a generator HG tilde built from only the green squares and achieving exactly your gate G. Now, the first condition is somehow given for granted, no? Given for free. I can only use my green squares. I don't have anything else available. So somehow that is easy to enforce. How about these two conditions? These are the two conditions. So condition 2 and condition 3. This is where the problem starts. So meeting them analytically can only be done in some very well-educated situations, okay? So there are instances where you can achieve these two conditions analytically, and they can therefore build an analytic form of HG tilde, but that's a very small number of cases. In general, I will have to plug the problem into a computer and solve it. However, these two constraints, condition 2 and 3, allow me to identify some starting point in the numerical optimization problem that I will have to face that will help me a lot in solving the problem effectively. In which sense? Well, that's the strategy. That's somehow the recipe that I will have to follow. What I'll do is that I'll pick up the new generator, not the effective generator, HG tilde that I want to construct, build it from gate taken from the set of allowed transformation only. Then I use the second condition that I have illustrated, so the commutativity, the commutation between HG and HG tilde, to reduce the set of possible elements from lambda that get into, from gamma, that get into my HG tilde. This will constrain the number of parameters that I will have to use in order to parameterize the generator HG tilde. And then I will only have to solve the third problem. So ensuring that the eigenvalues of the difference between my parameterized HG tilde and HG is 2 pi times an integer. The enforcing of this condition is equivalent to solving an inverse eigenvalue problem. And if you are versed with computer science, you know that inverse eigenvalues problems are complicated to solve. And in general, we don't have an analytical way of solving inverse eigenvalue problems. That's where I'm using supervised learning. So we will use a supervised learning approach to solve the inverse eigenvalue problem embodied by condition 3 in my three bullet point recipe. So I'll decompose my generator over a basis of operators OI that are allowed. So OI here are the gates, the allowed gates that I take from set gamma. I will look for the fidelity between the state resulting from the application of this effective decomposition of the generator and evolving it. So psi here is a generic input state, and the actual gate G that I want to synthesize. So this quantity F here is basically the similarity between what I want to achieve, the target gate that I want to achieve, and the synthesized object that I can build. So basically the comparison between some inspired chip, desired pirate chip, and what he is able to achieve by putting together his 15 bricks from Lego. Then I will look for the parameters that make this fidelity equal to 1, regardless of the input state that I want to achieve, and this is that I want to feed into the calculation. And this is a crucial point. I don't want this fidelity to be 1 for a specific input state. I want it to be 1 for any input state, okay? So my gates, my synthesized gate should be the right one, regardless of the input state, not just for a special one that might work well. Great. How do I solve this problem numerically? So through my supervised learning approach, I make an initial choice for the set of parameters lambda that enter the decomposition of the generator over the set of allowed transformation. I generate a set of random input states psi k, with, say, for a very large number of elements of this random set. So NB here must be large. And for each of them, I compute the gradient of the fidelity when I vary the parameters of my decomposition, like a variational problem. And I update the values of these parameters, so of this vector of parameters, using momentum gradient. And which means I vary basically objects, so the parameters entering the decomposition of fidelity, using a momentum term and a learning rate that are two parameters entering standard machine learning methods for momentum gradient. And I will repeat that until a satisfactory value of fidelity is found. So if I find a fidelity of 99.99999, as many 9 you want after the dot, then I will stop. If you achieve a lower value of fidelity, you should continue until you achieve your threshold value. How do I compute this momentum gradient? I use standard classical machine learning methods, from PyTorch to TensorFlow, things that are very well established in basically say hundreds of codes for the solution of optimization problems based on automatic derivation. So let's look at the result for a couple of significant cases. So what I want to achieve is a Toffoli gate. And if you have studied your quantum information processing, your theoretical quantum information processing, you know that a Toffoli gate is a very important gate. It's a universal gate for quantum computation. If I have enough Toffoli gates, I can build up arbitrary transformations, arbitrary circuits for my register, for arbitrary large register. So it's an important gate. In practical terms, a Toffoli gate is a controlled NOT gate. So it flips the logical value of the bottom line in this drawing, conditioned on the logical value of the first two lines, which are called the controls of my gate, while the last term is called the target. So if the controls are both in the one state, then I will flip the logical state of the target, and I will do nothing if even one of them, one of the controls is in zero. Now, the generator of a Toffoli gate is the expression that you see here in the left-hand side of this slide. Sigma here are sigma x, y, and z are the Pauli matrices, and you can see I will need single body operations, like, I don't know, a single sigma z1. I will need two body operation, no? When I multiply sigma z1 and sigma z2 and the identity for the third particle, I have two body operations, but I will also have a three body term, sigma 1z, sigma 2z times sigma 3x. And I don't want that. These are difficult to achieve, they are complicated. I want to synthesize my Toffoli gate having at hand only two qubit terms, only two body interactions. So the set of allowed transformations that I want to use, gamma, consists of only two qubit terms. And this is the decomposition of at most two qubit terms of the generator of my alleged generator of my Toffoli gate. And if you count the number of parameters that you have here, as you can see, there is basically no interaction, the identity, single body evolution, a single Pauli operator, and two body operations, so no three body interaction at all. If you count the number of parameters that you have, you count about 37 parameters in this decomposition. Then what you do is what I explained before. You enforce condition 2. And as I said, condition 2 allows you to reduce the number of parameters in your decomposition. So if you enforce the commutativity between H Toffoli and H tilde Toffoli, then you go down to this expression, which contains 10 parameters at most. I don't know the value of them. I want to get them. And in order to get the value of these parameters, I should solve the inverse eigenvalue problem that I have illustrated a couple of slides before. Sorry. However, with 10 parameters, solving this problem is too much complicated. It's too complicated for me to solve analytically. So I use the machine learning approach that I have illustrated before. And this is the outcome that came from implementing that momentum gradient approach to the behavior of fidelity and the variations of the parameters entering the decomposition of the generator. And each line here represents an instance of the values that the set of parameters J entering my restricted decomposition of the generator can achieve. So for instance, if you follow the green line, the green broken line that you see in this plot, well, that gives you the value that J033 and J030, J330, and so on achieves for that solution outputted by my computer when implementing momentum gradient. If I pick up the values of the parameters given by the green line there, and I plug it into my H tilde Toffoli, I will get a gate that achieves a fidelity with a desired Toffoli gate that is 1 for any input state, even randomly picked up input state of 3 qubits. And I can do the same also for the Fredkin gate, which is another very important gate, again, a universal gate for quantum computation. It's a controlled swap gate. So this gate swaps the logical level of the second and third line if the first one, the control, is in the one state, logical state. Once more, if I decompose the generator of a Fredkin gate, I will have 3 body interactions. Once more, I only want 2 qubit terms. I follow the very same line of approach that I've illustrated before, and this is a result. This is one case that allow me to achieve in the very same way. So achieved through my machine learning approach to the calculation of momentum gradient and to optimization of the fidelity for any input state to my Fredkin gate. Again, multiple instances of optimal solution are possible, and even in time, you can track the behavior that the parameters will take, seeing that after a very short time, the algorithm is able to converge towards a stable solution. Great. Enough for gate synthesis. Let's have a look at what we can say about quantum state engineering and the validation of quantum states, okay, and their properties. And the work here is the result of combination of efforts between my group in Palermo and Belfast and the Sapienza group led by Fabio Sciarrino in Rome, and with some collaboration coming from the University Federico II in Naples, in particular the group of Lorenzo Marrucci. So I will illustrate that theoretical approach and also some experimental result. And the ingredient that we need in this context is a quantum walk. And I'm sure that at least someone in the audience, whether remote or in presence, would have seen already the dynamics of a quantum walker. Everyone instead is very well versed, I'm sure, and very well familiar with the dynamics of a classical random walker, right? So basically, if I toss a coin and I get head, I will move the walker to the right. If I get tail, I will move the walker to the left. When I move to a quantum domain, the coin can be prepared in a quantum superposition of head and tail, which means that every step of the quantum walk, I can take the walker and move it to the left and the right at the same time, in a sense. And this realizes a dynamics, an evolution. So these are the 2 examples. So again, if the coin is up to the right, if the coin is down to the left, but the coin is also a superposition, so I can get superposition of walks to the right and to the left. Now, if you look at these dynamics from a merely mathematical viewpoint, basically you have an n-level system, no? So the walker can occupy, for n step of your walk, can occupy 2n or 2n plus 1 different positions along a line. So what I have is a n-level system, so to say, is the equivalent of a spin n. The probability with which I will occupy the various levels, logical levels of these spin n particle goes not like that, the distribution of a standard random walk, which is this Gaussian that you see on the left, but according to these, say, Batman hair ears-like distribution. So a distribution where my population, no, sorry, my probability of occupying a position is large towards the end of the chain. So this is a simulation for 100 steps and is flat at the center. So a radically different distribution than the classical random walk. But what matters for what we are concerned is the analogy between the dynamics of the quantum walker and the spin n particle. And my question is, can I prepare an arbitrary state of my walker, of my spin n particle, using the interaction between the walker and the coin, and the quantum coin? So can I design a proper way through which the walk takes place that achieves a desired state of my spin n particle that I'm using as an analogy for my quantum walk? And the answer is yes. Once more, using a machine learning approach, one can retrospectively find which is the best state preparation for your quantum coin, step by step of your walk, and which is the best parameter of your coin. So basically, what determines whether the probability that your particle, that your walker will move right or left in the walk in such a way that you give me the desired spin and state, and I will achieve it with unit probability. So machine learning, once more, helps us understanding or identifying the set of parameters, a very large set of parameters that I need to engineer in order to achieve a problem successfully, a problem of quantum state engineering. And the beauty of this approach is that the experimental team in Rome was able to implement it in a photonic platform. Okay, so they run precisely the experiment that I have illustrated before through my stupid cartoon. What they have is the use of 2 degrees of freedom of light, polarization, embodying, so to say, encoding the degrees of freedom of the coin, and orbital angular momentum, which is basically the shape of the wavefront of a light beam. So by engineering different shapes of the wavefront of your field, they are able to achieve a given state of angular momentum, which means spin n, a spin n state. The problem now is how do I couple them so that I can achieve the quantum walk dynamics, no? So the motion towards left or right, depending on the state of the coin that I will need in order to achieve the quantum walk dynamics. And the guys in Rome can do it through this QP object that you see in the sketch for the experiment. QP here stands for Q-plate. A Q-plate is an active medium, is an inhomogeneous active medium that couples orbital angular momentum and polarization and changes the value of the angular momentum, so the quantum number of the orbital angular momentum state, depending on the state of polarization of the light field. The transformation is basically represented by these 2 equations that you see at the center of the slide. So if I enter my Q-plate in the left polarized polarization state and with orbital angular momentum in state M, a Q-plate will generate a superposition of left polarization and state M and right polarization and state M plus 2Q, with Q a number that I can tune by adjusting the properties of my Q-plate. And if I get into my Q-plate with a state like R, right circular polarization, and state M, you achieve a similar transformation for that too. So what you should appreciate is that you have a superposition of left M and right M plus 2Q, which means you will achieve coherence in the orbital angular momentum states of light, depending on the state of polarization of the light field itself. So you are implementing exactly the sort of dynamics that you will need in order to implement a quantum walk transformation. So these guys in Rome, what they did was concatenating sequences of linear optics elements, quarter wave plates, half wave plates, and Q plates, so as to achieve the various steps of the quantum walk. And what they get in the end is precisely the ability of nearly perfectly engineering. I mean, nearly perfectly, I say that because there are experimental imperfections, needless to say, but nearly perfectly engineer arbitrary states of your orbital angular momentum, your quantum walk. So for instance, in the block sphere that you see there is a generalization of the block sphere, is a Poincaré sphere. We engineered 4 different states. We engineered state plus or minus 5 in a 5-step quantum walk, or superposition of plus 5 and minus 5 according to the various arrows that you see on the sphere. And the leftmost diagram is the distribution of populations that you see for each state. for each of the 4 states that have been engineered in the Rome experiment. And this plot here shows the fidelity with which the states have been achieved. So you can see, say, for instance, for a specific one, for the blue-colored one, which I forgot which is, but for the blue-colored state that we have seen in the previous slide, we achieve it with a fidelity of 97%, limited solely by experimental imperfection. Yeah, for those of you that are curious about that and like the mathematical aspects of it, well, the horrible diagram that you see, or interesting diagram that you see on the left-hand side, is the phase space distribution of these spin end states in cylindrical coordinates. Okay, property validation. Okay, and this will be the last 5 minutes of my talk, and a different take altogether to the use of machine learning for state engineering, for property engineering. So there is something in machine learning which is called reservoir computing, which is a very interesting approach to the processing of information. So basically, you take a classical reservoir of particles that are connected, classical particles. So this is all classical at this stage, okay? So these are classical particles coupled to each other in some way, so scattering information according to some arbitrarily given adjacency matrix, so way to connect these particles together, and that I don't know, right? So we don't want to know. It's a reservoir in this sense. It's something that I do not engineer, I do not control, I do not put together. Someone gave it to me, okay? And I don't want to poke it, okay? So I don't want to discern, to understand how the various green balls that you see there are coupled to each other. I want to use this classical reservoir to understand what is the image, to learn what is the image representing my classical input. So this picture of a cat on the left-hand side. So what I will do is that I will couple the pixels of the image to every particle of my classical reservoir. This information gets spread across the network of green balls, the reservoir itself. And then what I do, and this is the machine learning part of the protocol, is that I take some of the particles of my reservoir, is what I call the output layer. I measure, so I acquire information on them, and I train this output layer in a way that I am able to reconstruct the information encoded in the reservoir about the input. So reconstruct the classical input that I had at the start. So the difference between a reservoir computing approach and a standard neural network is that I don't train the network at all. I don't change the couplings. I live with the couplings that have been given to me. What I do is that I train the output layer only. I perform a standard, a very simple linear regression on the data that I acquire from the output layer so as to reconstruct the input information. When I somehow extend the problem to the quantum domain, I have various ways of doing it. One way is extending the reservoir of classical particle to quantum particles, okay? Quantumly connected particles. So I achieve a quantum reservoir. And the other way is to move from a classical input to a quantum system as an input. So many quantum particles or some quantum particles prepared in a quantum state as input to be reconstructed. So now you understand what the problem of quantum reservoir computing is. I want to use a quantum reservoir, a network of connected particles that I do not want to control, to learn something about an input, a quantum input state. And I do that by measuring some of the particles of the reservoir, the output layer that I was talking about a few minutes ago, acquiring classical information through a generalized POVM, that's okay, that I will then use to train the network and reconstruct through a linear regression process the properties at the input of my reservoir. Great. Don't worry about that. Again, in a collaboration between my groups in Belfast and Palermo and the Sapienza group in Rome, we have implemented this approach in a photonic experiment to achieve the following. Suppose that you want to learn information about the polarization state, the unknown polarization state of a light beam. And I do that without having to reconstruct the state of my polarization degree of freedom. So I don't want to make a tomography of the polarization state of light. What I want to do is to use a reservoir computing approach to learn about the polarization state, the unknown polarization state of my light field. So I exploit precisely the interplay between polarization and orbital angular momentum that I made use of in the state engineering part of this part of my talk, of this section of my talk, and I will use as a network, a reservoir for the learning of the polarization state of my light, the orbital angular momentum of the light field, okay? So I will couple polarization to different states of the orbital angular momentum. I will connect them in a say through my photonic reservoir. I will measure the orbital angular momentum state of light, train that information so as to reconstruct the polarization state of my field. Now, the state that I want to reconstruct is the state psi that you see there. The unitary decoupling between input and reservoir is given by this gate U that you see, this transformation U that you see in the middle of the slide, and that's implemented in exactly the same manner as I said before. So Q plates coupling orbital angular momentum and polarization, and then linear optics elements. And we use two Q plates to reconstruct the property of polarization, as you can see here. So what I show in this diagram is basically the expectation value of 3 Pauli operators for the polarization state of my light as I change the number of states that I've used for the training part of my method, of my algorithm. What you can see from this diagram is that after about something like 5 training states, so a training set of about 5 elements, so a very small number, the error in the reconstruction of the expectation value of either sigma x, sigma y, or sigma z drops down to very small values, no? At least 10 to minus 1, but all the way down to 10 to minus 2 for sigma y. So I'm basically able to reconstruct with a very high level of accuracy the expectation value of the 3 Pauli operators for my polarization state. So I'm able to acquire information on the state of polarization of my light field without having to control at all the coupling between the reservoir, the orbital angular momentum, and the degrees of freedom that I want to investigate, the quantum input that I have at hand. Great. With that, I think, yes, I want to skip this part and I can go directly to my conclusions. So I hope I've convinced you that there is plenty of room in the combination, in the admixture of quantum dynamics and and machine learning, in particular reservoir computing, when you are interested in photonics quantum computation. And there is plenty of room for having fun. In doing that, I should thank the bodies that have put the bread on our table, the groups in Palermo and Belfast that suffer my complaints and tantrums, and I thank you for your attention. Before putting some shameless advertisements, so there will be a number of positions in my group in Palermo to work precisely at the interface between machine learning and quantum dynamics. So if you are interested in joining us in Palermo, or you know of anyone that might be interested in joining us in Palermo, please point them in my direction. I will be grateful. Thank you for your attention, and thank you for your patience.
Thank you very much, Professor. Do you have any questions? Yes.
Greetings, Mauro. Hello, this is Özgür.
Hello, Asgur. How are you?
Great. Thank you being with us. Thanks a million for joining us. It was fantastic to listen and learn from you again.
Thank you for having me.
Thank you. I have a few questions. First of all, it was great to see Sammy, and I'm sure he's growing. And yeah, this is the same old pictures. So probably these Legos could be old and errorless. So if some of the Lego pieces has some errors, would your method be able to detect and eliminate them at the end?
Yes, so we made a number of, I didn't present it in the slides, but we made a number of numerical simulations of what happens if the Lego bricks, so to say, have an intrinsic error, okay? So if instead of having exactly the transformation that I think I will need, I have something slightly different. And what we found is that even in the presence of errors in the Lego bricks, so to say, I am able to synthesize a pirate ship with unit fidelity or arbitrarily close to 1 fidelity, regardless of the input state of my system. So the approach seems to be robust against errors in the implementation of the transformation in the gamma set.
Thank you. Still buying him a pirate ship.
I'm too stingy.
Second question is that you mentioned in this quantum walk there is orbital angular momentum is interacting with the polarization. Is it like a structure like with spin-orbit coupling?
Absolutely so. So the quantum walk dynamics indeed establishes basically a highly entangled state between these n-level system, the orbital angular momentum or the walk Hilbert space, and the Walker Hilbert space, and the polarization degrees of freedom. So you end up with, in an ideal case, you end up with a qubit entangled state. And that is in a way, the resource that you exploit in order to then project the state of the orbital angular momentum in a given state that you might want to achieve. Okay, so the answer to the question is yes, you achieve a very high degree of entanglement through these dynamics.
Great, excellent. And the last part of the talk, can you do a little bit more marketing? The method is very impressive with this, because I think the competition is with the quantum state tomography still. So what would be the main advantage relative to this more established?
Okay, very good. Very good. So as far as I'm concerned, as a theorist, the main, but my experimentalist friends agree with me on that. The main advantage is in the simplicity of the measurement strategy. So all these guys have to measure are populations of the orbital angular momentum states. And that's really, really trivial. So the classical information, maybe I can share again my screen and show you. The orbital angular, the measurement that I will have to perform here. So the measurements that I have to perform here, okay? So the output layer is probed only in terms of the probability that the orbital angular momentum is in one of these 5 states. I don't have to measure in complicated rotated bases that superimpose states of the reservoir. So there are trivial measurements that these guys can do, and they can do with very high accuracy. So they are really easy for them, and that simplify the procedure. First. Second, I don't need to engineer the coupling between the light field, so the polarization, and the orbital angular momentum. So the various wave plates that you see here in the experimental apparatus, they have been put in the experimental setup at random. So I don't need to know how they are coupled. I don't need to control the dynamics at all. The polarization and orbital angular momentum evolve together, but in a way that I don't control at all. I perform this set of very simple measurements at the output after an uncontrolled dynamics, and I achieve a fantastic accuracy after a training with only five 5 input states. So major experimental advantages that make this approach a lot more convenient than state tomography. And what we are doing now is to scale up the dimensions of the problem, so to say. So we are moving from single state of polarization to entangled state of 2 polarization degrees of freedom. So two light fields in an entangled state. And what we want to reconstruct is not the expectation value of local observables. We want to reconstruct the degree of entanglement. And we have some preliminary data that show that with only these sort of very simple measurements that we are implementing, and again, without controlling at all the dynamics between orbital angular momentum and polarization, we are able to reconstruct the entanglement, the degree of entanglement at the input, implement even some entanglement witnesses with errors that scale very, 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 very favorably with the size of the training set. I don't know if I'm answering your question, Osgur.
Oh yeah, you're right. Amazing. So I am also talking with experimentalists on biophotonics, and QST is what we were using, and this is definitely opening new directions. I will be in touch more on this actually.
Absolutely. Delighted to talk about that with you.
Yeah, okay, so thank you so much. Again, hopefully you will be physically with us in near future once you settle down in Palermo.
It will be beautiful to have you here, and thank you so much for your attention, guys. Thank you.
Bye-bye.
Bye.